Dear students, welcome to EPG Pathshala. This module is in continuation of the previous module, that is Introduction to Time Series and its importance. After that we discuss about measurement of secular trend and measurement of irregular, seasonal and cyclic variation. In this module we will give you basic introduction to stationary time series. Stationary time series is a very important component for future forecasting purpose. So in this module we will first give you introduction about stationary and its two different types, that is strictly stationary and weakly stationary. After that we will give you some basic definition, that is autocovariance, autocorrelation and other definition also. So let's get started with this module, Introduction to Stationary Time Series. Since time series analysis has wide application in the practical world, then the question that come to the mind are, what is the purpose of using this tool? Why time series analysis is considered as the most important tool in the financial field or other areas? How this analytical tool is considered as more useful than any other methods? Many of these types of questions will be in your mind. We will try our best to answer all these type of questions in this module. It is very well known from the module Introduction to Time Series and its importance about the time series and how to measure its component. We are rewriting here again about time series. What is time series? Time series is a sequence of observation that record the data at regular time interval, such as retail price index. The main purpose of using this analysis is for the description of the data. Second is the construction of the models which fits the data, forecasting future values. Let's say a business analyst wants to analyze the future situation of the company. First step is to analyze the previous year's figure, so that using those figures they will be able to comment on it. Now, in the most practical situation, observations data relies on time. In these situations, time series analysis is more useful. Linear regression analysis is also considered in forecasting, but it is less useful because it considers the relationship on one variable with another variable, such as hours spent in a day, for study correlated with the marks scored, or yield of a crop depends on other factors, etc. The main thing in regression analysis is that here observation values may not be observed with time, but in time series observations are observed with time. Therefore, it is important to understand the relationship of variable over time. For example, the price of share increase or decrease with time. Here the weather condition on a particular day depends on its previous day weather. Hence, it is important that one should study the relationship of a variable with its previous value through modeling. That not only helps in the fitting of data in more appropriate manner, but also for future predictions. Time series analysis is used to understand the behavior of any variable over time. Time series analysis consists of different techniques, theory and method to predict the future value based on previous observed value. This prediction theory is therefore classified as time series forecasting. Time series analysis and forecasting have wide applications in different areas. Time series analysis is mostly used in business and economics area. Some other application areas are weather forecasting, pattern recognition, earthquake prediction, mathematical finance, etc. Now come to time series as a stochastic process. A time series is a stochastic process because time series is a sequence of observation, and sequence of observation is basically a realization of sequence of ordered random variables, that is stochastic processes. Now come to definition. Stochastic process is families of random variable which are function of, say, time. A stochastic process is also known as random process or random function. It is denoted as sequence of yn where y is a random variable at time n, and n takes value from greater than 1 and so on. Basically, it is sequence of random variables that model the value of process at time n. Now, the second definition is a time series process is a process indexed in discrete time and continuous state space. It means we are taking time on discrete time point and it take value in a continuous manner. So, for example, daily closing price of a share market, here daily is considered as a discrete component, that is days, and the value of a share price is considered a continuous value. Such series can be written as this in this form. So, in general terms, stationary means stability. In time series analysis, stationary means stability of the stochastic process with respect to its random variable. It means there is no change in the time series with respect to changes in the time interval. This is known as time series analysis. In literature, there are two types of stationary. These are strictly stationary and weakly stationary. Definition of strictly stationary is stochastic process is said to be stationary or strictly stationary times if joint distribution of random variable, that is y subscript t1, y subscript t2 and so on, y subscript tn and y t plus k1, y t plus k2 and y t plus kn are identical for all t1, t2 and tn, and k1 plus t1, k1 plus tn in J and all integer n. This means that all statistical properties remain constant as time elapses, that is mean, variance and covariance of the process remain constant. A white noise series is stationary series with mean 0 and variance sigma square. Now, this is a graphical representation of strictly stationary. So, in the graph you can see that all the observations lie above, mostly above the line or below the line. So, this is example of stationary time series. If the graphical representation of any time series is same as the above shown image, then the time series is known as stationary time series. Although it is not a good method to check about the stationary of any given data, one has to use the properties to test about the stationary of the data. Example, let un is the independent and identically distributed standard norm or random variable. Show that the following process is stationary time series or not. So, we have to prove that whether p subscript t, that is a stationary process, and we have to see whether this process is stationary or not, and it is given as cos of wt plus ut. The solution is, first we have the information that ut is independent and identically distributed random variable. So, it means expectation of ut should be is equal to 0 and variance of ut should be is equal to 1. To show stationary time series must be constant, we first have to expand the cos of w function of cos, that is cos of a plus cos of b, that is cos of a cos of b minus sin of a sin of b. Then we have to take expectation. As we have information that expectation of ut is equal to 0, so expectation of cos of ut is also equal to 0 and expectation of sin of ut is also equal to 0. So we will get the answer that expectation of cos of wt plus ut is also equal to 0. And similarly, as we know that the covariance of any two random variable is equal to the product of random expectation of product of random variables and their product of individual expectation. So, here covariance of pt and ps is also equal to 0, where t is not equal to s. Hence, one can observe that the mean and covariance values are constant. So, given series is said to be stationary time series. Now, come to weakly stationary. A stationary or strict stationary condition does not hold in real life, because there is no necessity that all the properties, that is mean, variance, are constant with with respect to time. So to overcome the problems of strictly stationary, another type, that is weakly stationary time series, is introduced. So definition of weakly stationary: a weakly stationary time series require that mean and variance of the process remain unchanged at time elapses, but covariance depend on its time difference, that is lag. So we already discussed that covariance of yt and ys and yt is represented as this form, where ys and yt are the random variables that models the values of the process at time s and t respectively. This covariance depend on lag of time difference, that is t minus s. Example: let ut is the independent and identical distributed standard normal random variable. Show that the following process is stationary time series or not. Also check that it satisfies the properties of weakly stationary process. So this is our process, that is pt is equal to u of t minus 1 plus u of t. We have to check whether our process is stationary, and if it is stationary then it's fine. If it's not stationary, then we have to check whether it satisfies the properties of weakly stationary or not. So this is solution. First we have to take expectation and take covariance also. So we can see that expectation of pt is equal to 0 and covariance is given as 2, but this is of lag 0. It means we are taking covariance of pt and pt. So this is equal to variance of pt. Time series has constant mean and covariance changes as time difference changes. This covariance value at lag 0 is 2. Now if you take find out the covariance of pt with with lag 1, that is pt plus 1 or pt minus 1, then the answer will be 1. So covariance value for lag greater than 2 will be 0. So one can see that as time interval changes, covariance value changes, that is covariance depend on the lag or time difference. So this process is not considered as stationary one, but we can see that from the properties of weakly stationary that it follows the properties of weakly stationary time series. So this process is weakly stationary time series. Now come to the definition. Autocovariance function: the covariance between any pair of elements of same variable of a stationary sequence depends on its lag difference. This covariance is known as autocovariance. The autocovariance function is defined as gamma k, where k is an integer of a stationary process. Y is defined as follows. So here gamma k is equal to expectation of yt and yt plus k minus expectation of yt and expectation of yt plus k. So gamma, and also the gamma of k is also equal to gamma of minus k. Here there is no difference between the lag, whether you are taking covariance between yt and yt plus k or covariance between yt and yt minus k, but the result only hold for the stationary time series. So if k equal to 0, autocovariance is converted into simple variance, then you know that as we have the stationary series, so in that case most of the cases we have variance is equal to sigma square. So in the stationary process, the mean are constant and covariance are function of time lag. So the covariance between two variable remains same as have same lag, that is time difference. Hence in the autocovariance function there is no need to mention about the starting time, because it is necessary to mention time lag only here. On the other hand, if a process is not stationary, then the autocovariance function depends on two variables. First is time and second one is lag k. It means that covariance of variable changes with time although having same lag. Then the notation for the autocovariance is defined as gamma t comma k, that is covariance of yt and yt plus k. Here gamma t comma k denotes the covariance between yt and yt plus k for non-stationary time series. Now come to the definition of autocorrelation function. The autocorrelation function defined on squared unit, so it depends on absolute size of measurement. We can make it independent of the absolute size of yn by defining a dimensionless quantity. The autocorrelation function for a stationary series defined as rho k, which is equal to proportion of gamma k divided by gamma naught. And in the similar manner, rho k is equal to rho of minus k, that there is no difference between whether you are taking lag of k or k plus 1 or k plus t and k t or t minus k, where rho k is called the autocorrelation function with lag k. The autocorrelation function of a purely interdeterministic process satisfies rho k converges to 0 as k tends to be finite. It means that as we increase the time lag between variable, then the autocorrelation between the variables converges to 0, that is there is no relationship. If the process is stationary, then we have the different notation for autocorrelation like autocovariance. The autocorrelation function for a non-stationary series is defined as given here. Now come to definition of correlogram. Autocorrelation function is the most commonly used method to study the relationship between variable at different time period in time series. One can derive a lot of information about a time series from a plot of a sample autocorrelation function on one axis and lag on the other axis. This type of plot is named as correlogram. Now come to definition of partial autocorrelation function. It is an important characteristic of a stationary series. Partial autocorrelation function is the conditional correlation of yt plus k with yt, given yt plus k and so on yt plus k minus 1. It means that in the partial autocorrelation function is the autocorrelation function between two variables by fixing the values of other variable. Partial autocorrelation function can only be defined for positive lags. The values of the partial autocorrelation function may be derived as the coefficient phi of k comma k in the following equation. So one can find out the partial autocorrelation function for lag k by solving this equation. So one can find the value of partial autocorrelation for small lag, but for large lag value one has to take help of statistical softwares. So what is now come to definition of parsimony principle. So while building a proper time series model, we have to consider the principle of parsimony. According to this principle, always consider the model with smallest possible number of parameters to be selected for representing an adequate time series data. Out of most suitable models, select simplest one because complicated model has large number of parameters. Large number of parameters show overfitting of model. Overfitting is not suitable for future forecasting. So for future forecasting of time series model, we select most parsimonious model among all the possibilities. Now we will discuss different types of stochastic model. Basic introductory time series model, that is multiplicative and additive model, contain array terms in terms of irregular component, but this component is not random. Array term must be considered as a random quantity because variation in real life problems are random. So by adding an array term in the time series model, the basic model of time series is turned into stochastic time series model. The selection of a proper model is extremely important as it reflects the underlying structure of the series, and this fitted model in terms is used for future forecasting. These stochastic models are based on the assumption that corresponding time series must be stationary time series. In general, time series data can have many forms. Different stochastic process models are used to fit the data. There are some linear time series model that is used mostly in literature. These models can only be used with stationary time series, such as first is autographic model. Autographic model explains the current value of random variable yt as a linear combination of its parse value with additionally externally generated random variation. For example, current price of a commodity is based on the previous prices of the commodity, and ARP denote the autographic model of order P. Model for a random variable yt is defined as mu plus summation, where summation over alpha I yt minus I minus mu, where summation is over I equal 1 to P plus error term, where mu is the constant value, alpha is our autographic coefficient, Et is the white noise process with mean 0 and variance sigma square. So here Et is also is a random variable that follow normal distribution with mean 0 and variance sigma square. If we take P is equal to 1, then autographic model of is known as first order autoregressive model, and it is noted as AR1, and it is defined as yt is equal to mu plus alpha times yt minus 1 minus mu plus error term. So if you keep on substituting the values of previous yt in this in the model of ARP, then we get yt is equal to mu plus alpha raised t into y naught minus mu, and summation is over j is equal to 0 t minus 1 alpha power j et minus j. So now come to second model, that is moving average model. Moving average model arising from the current value of the process resulting from the recently passed random error terms as well as the current one. For example, disaster kit sales go up before and natural disaster go down during the disaster period and just jump again as people realize that disaster kit must be kept for security purpose from the natural disasters. So it is noted by MAQ. For sequence yt is defined as yt is equal to mu plus et plus b summation over j is equal to 1 to q bj et minus j, where et is a random error term, q represent order of a sequence, mu is a constant term, and beta j's are its coefficient. Now if you put the value q is equal to 1, moving average model will be denoted as MA1, and it is defined as yt is equal to mu plus et plus beta times et minus 1. Now autoregressive moving average model. Autoregressive moving average model is a combination of autoregressive and moving average model, so it depends on the past values and current values. For example, prediction of stock prices about future values in any stock market. One can use this model, that is ARMA, and it is noted as ARMA P comma Q, and that is equal to yt plus is equal to mu plus summation is over I and alpha I yt minus I minus mu plus et plus summation is over j, where j vary from 1 to q beta j et minus j, where mu alpha I beta j are constant and et is an error term. Now to test the stationary, we have two procedures. One is you can test the stationary through ACF or PCF. So to test for stationary in the recorded data, one can use correlogram. Correlogram uses ACF and PCF value to show values of parameter for the stationary stochastic models. If a correlogram show autocorrelation function decreasing geometrically towards to 0 and partial autocorrelation function is 0 after k is equal to 1, then y is a stationary series of autoregressive of order 1. So you can easily see from the graph that autocorrelation function keep on decreasing geometrically and partial autocorrelation function decrease to 0 after 1 k is equal to 1. So we can say that then this is example of autoregressive of order 1. Now in moving average of order 1 process, ACF coefficient becomes 0 after 1 lag and PCF declines geometrically towards to 0. So similarly similarly as AR1, we can see that for MA1 now the geometrically decreasing rate is for PCF, and ACF value can take value 0 after 1 lag. So this correlogram can be shown by using statistical software and programming. One can construct these type of figure using computer softwares like eViews or SAS, etc. So this is an example. So in this example we want to check the stationary of the data, and data is of daily total female births in California in 1959, and the link is given here to help you to see the data, and one can download the data set from the given link for the daily total female births in California 1959. So to check stationarity, one can use two types of method. First one is graphical method and second one is correlogram method. Here we are discussing both type of method to check stationarity in the given set. Graphical method, in this method graph plotted between given data set of daily total female birth in California and every 12 months. So from the graph you can see that there is stationarity in the time series. This graph show random sequence is constant mean and variance, so this process of time series stationary time series. Now we want to see the stationary of data using correlogram method. Correlogram method use ACF and PCF value of the given time series. If the autocorrelation function values are exponentially decreasing and PCF value value rapidly goes to 0. This time series stationary time series and fit autoregressive model. Parameter of the autoregressive model can be defined by the PSF value. After that, lag value, all PSF value goes to 0. That PSF value is the parameter of the AR model. If ACF values rapidly goes to 0 and PACF value exponential decreasing, then this time series is stationary time series and fit moving average model. Moving average model parameter defined according to ACF value. So this is the graph of cologram, and this cologram show ACF value exponentially decreasing and PSF value rapidly goes to 0 after 2 PSF value. So this is the AR model with parameter 2, that is daily total births of female in California in 1959. Time series is stationary time series and fit the AR2 model, stochastic time series model. Now we are going to sum up this module what we have learned. So in this module we give you basic introduction about stationary time series and its importance, and we discuss about two stationary time series, that is strictly stationary time series and weakly stationary time series. And after that we give you some definitions like autocovariance, autocorrelation, cologram, parsimony principle that helps to determine the stationary time series. And after that, types of stochastic model we discussed, that is autoregressive model, moving average model, ARMA model. An example is given in this module to help you understand how you can fit any particular type of model on a given given data. So basically this module will help you to understand the stationary time series in a very easy manner. So thank you.